Hello and welcome to this course on machine learning. We will continue with our discussion on nonlinear separation using neural networks. So recall that a single node neural network corresponds to a perceptron, and we saw how you could get separation for a function like OR using the perceptron. Basically weights of 1 and 1, a bias B of minus 0.25 and threshold of half. By making the bias more negative while retaining the same weights and the same threshold, you can actually get an AND, which is turned down only if both x and y are 1 each. One can also simulate a not x or not y using perceptron. So this not x or not y is obtained by multiplying a minus 1, a negative value, to the input x, and again a negative value to the input y. So for all practical purposes it is the same as an OR except for the multiplication. Now what do you expect this to give you? Well, this should be off only if both x and y are 1, and that is indeed the case. If both are 1, you get minus 2 plus 1.75, which is certainly less than half. For all of the cases the value is going to be 1. How about not x or not y and x or y? So this is the well known XOR function, and let us see what it looks like. So it is turned on if either x is 1 and y is 0, or y is 1 and x is 0. So this is the case when y is 1, x is 0, or x is 1 and y is 0. Otherwise, for y is 1, x is 1 and y is 0, x is 0, it is turned off. So you are trying to learn to classify between the plus and the minus. What you realize that a simple linear separator is not going to work. Unfortunately, a single node perceptron, single node neural network is a linear separator. However, by its very design, you realize that you could get the effect of XOR through a combination or cascade of separators. So how about the following? Let us say we had one node for not x or not y, another node for x or y, and then we consider a third node which takes a conjunction of these two, that is not x or not y and x or y. So the specific focus for this third node is on the AND, whereas the focus at the first two nodes is on the OR. Of course, the first node also has a special emphasis on the NOT. So we expect that a cascade of linear separators which happen to be perceptrons in this case should give you this nonlinear separation. And what we mean here is something like this. So this region, these two regions would be the region of positives, whereas these regions marked in grey would be the regions of negative. This architecture, which consists of a cascade of such linear separators is precisely the neural network. And here's this cascade of perceptrons for XOR. We have set the theta threshold to be 0 with some slight modification to the bias. So what you see here on the top is negation x or negation y, and you can convince yourself that both when x and y are 1 each with a threshold of 0, you get minus 0.25, which should give you value 0 here with the g function. For all of the configurations you will get 1. Likewise for the lower perceptron you will see that it is x or y, and it is 0 only if both x and y are 0. So what you see here is we have pushed the threshold into the bias, made the bias somewhat negative here and increased the bias in the first case. What the third node does is an AND, so it is basically an A and B. Effectively you get the nonlinear separation for XOR using a cascade of linear separators. It is not a linear cascade, so there are two linear separators which put together to give you a third linear separator. And this is the general architecture of feed-forward neural networks. You have an input layer, this is the input layer. Each of the inputs is weighted and passed on, the weighted inputs are passed on to the hidden layers. There could be multiple hidden layers which are basically going to take linear combinations of the inputs and produce output using the activation function G. The outputs from these activation functions could further go into other hidden layers which we haven't shown here, but you could imagine that each of these nodes is in turn a hidden layer. Finally, the output from the some of the penultimate hidden layers goes into an output layer. The output layer itself could consist of multiple nodes. In this case we have 2. If you are interested in multi-class classification, you will benefit from multivariate output. So if for k classes, for k class classification, you would have f1 to fk. Note that we are making an assumption here that every input instance could have multiple classes labeled. So this multiple output nodes is especially useful for multi-label setting. So in the multi-label setting, any input instance could belong to more than one class. So label is the association of a class with an instance. How do you train such a neural network? How would you obtain the weights of the XOR? So given data D, let us say the data is of the form 1, 1, 0, and this is what you would have for a XOR, 1, 0, 1, 1, 0, 1, 1 and 0, 0, 0. So given this data set, how to learn the weights W for XOR? Now the key step here is picking a network architecture, what should be the number of perceptrons? What should be the number of hidden layers? Number of layers, number of perceptrons in each layer. For example, we discussed a single hidden layer and a single output node, a single hidden layer consisting of 2 perceptrons. The number of output units is clear, the number of classes, but what should be the number of intermediate nodes? The number of input units is always equal to the dimension of features. So a reasonable default is to have one hidden layer. This is based on findings that a single hidden layer can actually get you the effect of multiple hidden layers. In case you decide to have more than one hidden layer, you typically tend to have the same number of hidden units in every layer. With the advent of GPUs and the possibility of lot of large scale parallel computation, people have resorted to use of very large networks. It is found that very large networks, when trained with sufficient amount of data set, will tend to get rid of redundant components of the network. More about this when we discuss deep learning in practice. To continue with the discussion, the number of hidden units in each layer is generally a constant factor of the dimension of X. Again, this is based on empirical findings. For the rest of this discussion, we will use smooth sigmoidal function 1 plus 1 upon 1 plus e raised to minus s. This is a smooth approximation to the step function. We already discussed how to train such a single node sigmoidal neural network. We will not use the non-smooth step function primarily because it becomes very difficult to train owing to its non-differentiability. The algorithm used for training the neural network is the so-called backpropagation algorithm. The idea is to randomly initialize the weights across all the layers, implement forward propagation to predict the function for any input, and execute backpropagation. And you do this by computing certain partial derivatives, use gradient descent to try to minimize the non-convex objective, the error function as a function of parameters EW, and you do this so that the cost function has indeed reduced. You also resort to some random perturbation of weights W to avoid local minima. This is a very high level picture of the neural network training algorithm. However, what we will do in subsequent slides is build up this entire procedure. So intuition for backpropagation is that when you have a cascade of perceptrons, as in this case you have x, y and z, x and y get weighted by wx and wy respectively, and then the resultant sum, weighted sum, is again multiplied by wq. There is a weight associated with the third input wz for z, which gets summed in a weighted manner with q to give you the final prediction f. Now, how do you match the prediction f with the desired value? That is what we will discuss. So the desired configuration for the inputs was -3 for x, 7 for y and z, for z it was minus 5, for f it turned out to be minus 20. So you realize that the predicted value 1 is less than the observed value minus 20, is more than the observed value minus 20, beg your pardon. So how do you train your weights in order to match the f with what is desired? Should we increase or decrease wy, or increase or decrease wx to decrease the value of f? Note that it is only wq and wz that directly interact to give you f. The interaction at x and wy, x and y, is very indirect. So the idea of backpropagation is to reflect these indirect interactions with f into updates for wx and wy respectively. So the intuition for backpropagation is iteratively update the weights along the direction where the loss decreases, reflect these weight changes from the loss into the hidden layers. We will set some notation for backpropagation. We will denote the weights going from the L minus 1th layer of the network to the Lth layer of the network with the superscript L. So WL11 is the weight on the edge from the first perceptron in the L minus 1th layer to the first perceptron in the Lth layer. So in general you have wij, this wij goes from the ith node to the jth node here. There are SL minus 1 nodes in the L minus 1th layer, SL plus SL nodes in the Lth layer. We will denote the final layer, the output layer, by L. So the Lth layer is basically the output layer. Capital Lth layer has k output nodes corresponding to the k variate output. The objective that we will consider for fitting a network onto the data is the regularized cross entropy error function. So recall that there was the cross entropy error function which measured the discrepancy between the desired output y's and the predicted output sigmas. Now in this case the predicted outputs are all at the Lth layer. In addition, we have capital K outputs. So unlike the logistic loss which had a single summation, here we have two summations, summation over all the examples and a summation over all the outputs. In addition, we use the regularizer to avoid overfitting. This regularizer is the L2 regularizer. We have already motivated its inclusion through Bayesian inference or the map inference problem. Question is, how do you minimize this error? So we note that the intermediate weights which lie on edges from sigma I L minus 1th layer to sigma j in the Lth layer are Wijl, and these have presence only in L2 regularizer. The cross entropy error function reflects these W's very indirectly for all but L equals small l equals capital L, because the error function is directly related only to the sigmas associated with the final output layer here. So this is what necessitates backpropagation. So backpropagation is because of this indirect relationship of the intermediate Wijls with the final output. So specifically, if you were interested in looking at the partial derivative of the error function with any of the Wijls, you will capture this in three parts. You look at the partial derivative of E with respect to sigma jl, because Wijl reflects in sigma jl. However, Wijl reflects in sigma jl only indirectly through the sum. So Wijl is reflected in sum as follows: sum jl is summation of the sigma over the i's from the L-1th layer multiplied by Wij for the Lth layer. And as a result of this, one can actually compute the partial derivative of the sum with respect to Wijl more directly. As you can see, this will lead to sigma I L-1. So here is the detail. So the partial derivative of sum with respect to Wijl is sigma I L-1, which was already pointed out. The second component, the partial derivative of the sigma with respect to the sum, and that has been shown here. And finally, what about the partial derivative of E with respect to sigma jl? As we discussed previously, this is indirect for all the L less than capital L and direct for small l equals capital L. We leave this as a homework for you to realize, and we will build upon this discussion in the next class. We will specifically look at how the whole update can be done for a single example. What we have done here is dropped the summation of I equals 1 to m and focused on a specific example x and its corresponding output layer y1 to yk. We find that a lot gets simplified, several summations disappear. More about this in the next class. Thank you.